Okay, so the exact transport. So the exact transport equation for dissipation rate above essentially gives us processes in the dissipative range. But we generally care about larger scales than that. When we're talking about turbulence. So what I mean by that is, let's see. So I'm going to try and draw a picture here. So basically when we have turbulence, so there are these big scales, and then if we zoom in on what's happening at the very small scale, eventually we have energy dissipating to heat. So this is our Kolmogorov scale. All right, so the exact equation that we derived is essentially describing kind of the balance of how this happens. But we care more about this large scale behavior generally. Because these scales are where like airplane wings are, or vehicles are, or internal combustion engine parts live, right? Like obviously these small scales exist, but usually, especially when we're talking about simulations, we're going to refine enough that we don't really have to, we can ignore that part of it unless we want to do like very, very small scale things, but that would be more in the range of no longer turbulence, but like molecular dynamics type stuff. So like physics, chemistry, looking at the very microscopic scale behavior. Okay, so if we're assuming that we care more about the big stuff because we're engineers, and so probably we do, that means that instead of basing, so instead of basing our models for d epsilon dt on the exact equation, what's commonly used is essentially purely empirical. So basically the models for transport are entirely empirical. I spelled that wrong. Okay, so generally what we have is that the material derivative of epsilon is equal to the divergence of a turbulent viscosity over this parameter sigma epsilon times the gradient of dissipation plus a coefficient C epsilon 1 production times epsilon over K minus C epsilon 2 epsilon squared over K. Standard values for these coefficients are the following. So let me actually hang on. I should say one more thing. So I'm going to just define what turbulent viscosity is in this case, which we've talked about before, but this is C mu times K squared over epsilon. Okay, so our coefficients that we need values for are C mu, sigma epsilon, C epsilon 1, and C epsilon 2. Sigma K. Okay, and those values are the following. So we have C mu is equal to 0.09. C epsilon 1 is equal to 1.44. C epsilon 2 is equal to 1.92. Sigma epsilon is equal to 1.3. And these are all defined by Launder and Sharma in the 70s, 1974. Okay. So this is the kind of key result for that equation epsilon. That's what we'll use in the K epsilon equations. Which, let's go back to that. Very good. So this equation is what's paired with the transport of TKE so the dk dt equation to form the K epsilon model. Okay. There's also a K omega model that is popular. You may have seen it if you've done popular. You may have seen this if you do CFD. Have you seen this one? So this is often like a choice in Fluent as well. K is still turbulent kinetic energy. And then omega is K over the turbulent viscosity. And it is referred to as a specific dissipation rate. Not spicy, specific.
It could be spicy, depending on how turbulent it is.
You never know. Okay. Okay. So to recap, since it feels like we talked about this 500 years ago, both K epsilon and K omega models tend to perform well. Perform well for separated flows. Okay. Cool. Since we are finishing up turbulence today, I can't not tell you about things that happen near the wall. Okay, so when there are walls in a turbulent flow, there's some important considerations that need to be made, which is often called the law of the wall. We're very dramatic
Sounds very
sometimes.
ominous, yeah.
Yeah, Jon Snow is not there. You guys not watch Game of Thrones?
No.
Oh, no.
Not a lot.
Oh, so sad. Okay, sorry. Maybe someone on the internet will appreciate that. Anyway, okay. Okay, so we're going to talk about law of the wall. Which almost rhymes, but does not. And this is developed by, oops. Von Karman originally. And yes, that is the Von Karman of the Von Karman vortex streets. And also Coles later in the 50s. And essentially what this does is it says that there are two self-similar regions and then kind of a buffer transition between them. So this postulates that there exist two self-similar regions and a buffer layer between them. Okay, so we are going to do some dimensional analysis, essentially. So our wall variables are the following. So we have U tau is equal to the square root of the shear stress at the wall divided by density. And then we define a dimensionless coordinate. Y plus is going to be U tau over nu viscosity times just the regular coordinate system y. Okay. And then similarly, we have a U plus dimensionless velocity, which is just our standard velocity normalized by U tau. Okay. Okay. So we are going to essentially define these layers of the flow relative to our y plus dimension. And I'm going to draw a picture that is going to represent what experimental data looks like. So do that a little better. Oh, that's better. Okay, so our horizontal axis is going to be y plus. And then our vertical axis is going to be our bulk velocity normalized by y plus, or by u plus, sorry. All right, and so what we observe happening in experimental data is we have this parabolic kind of shape followed by a curving over like this. And then the data will kind of pick back up over here. All right, so this is all, imagine that this is experimental. Okay. This is experimental data, is all going to look like this. And the way that we kind of break these regions apart is we have, we can kind of draw this shape here. And then we can also notice a linear region here. And so we divide this up in the following way. So before this picks up again, actually. So beyond this point, outside of here, this is considered the outer region. Nope, I lied. I'm going to divide this up slightly, hang on, slightly differently. It's going to erase this whole line. Okay, so I can kind of separate off this tail that picks up from that linear curve. And then I can also identify this early portion of the curve where it's kind of linear looking. And then I can also split off another section that is approximately linear as well. So in between these two, this is what's referred to as the buffer layer. The leftmost section here is our, no, I already used blue, is our viscous sublayer. And then after the buffer layer, we have a logarithmic layer. And everything beyond the buffer layer is generally referred to as the outer region. So over here, this is our outer region. And then this, bless you, is our inner region.
They overlap.
Yeah. That was why I was getting turned around initially. I was like, wait a second. So the logarithmic layer is kind of shared. It's sort of like a transition. Okay. Okay, so the inner, let's talk about each of these layers in a little more detail. So the innermost layer the viscous layer or laminar layer exists is between 0 for Y plus to around 3 to 5 Y plus units. Okay. It's assumed to be dominated by viscous effects. AKA not turbulent effects.
Basically, just because the resistance to shear is enough to damp the turbulence.
Yeah, it's going slow during or really close to the wall because of the boundary condition.
Okay, so it's actually a no slip it's a no slip and impermeable side of things versus the actual viscosity itself.
Well, both.
Okay.
Yeah. The viscosity is going to change how quickly the flow will, become non-viscous, right?
Yeah, but it's basically just some functions with it. It's such a sharp, whatever, it's such a low velocity that at that point it can't actually get turbulent to that point because it's no slip.
So it all kind of is baked into U tau.
Okay.
Right? Because the shear stress depends on the viscosity.
Yep.
Okay. And in this region, I kind of already mentioned this, but it has a linear velocity profile we have a linear velocity profile very near to the wall. Okay. This layer is very thin. All right. And resolving it in simulations requires at least a few wall normal grid points in the laminar sublayer. So if you are doing resolved turbulence flow that's wall bounded and you're at a conference, if my PhD advisor is there and many other people, they will ask you what your grid spacing is near the wall in terms of Y plus. For example, let's do so for example, if we consider a Cessna 172, I forgot an S. There's two S's. That still looks wrong, but it's not. Okay. So this is an airplane, like private pilot kind of airplane, that is flying at a speed such that our Reynolds number is about 6 million. And the chord of the wing is about 1.5 meters. Given that, we have y plus equals 1 at 0.006 millimeters. Very small. Okay, so our viscous sublayer is 3 to 5 times that very small number, right? So if we were to want to fully resolve this simulation, that would be insane.
So you got some computers that can do it.
But why?
That's fair.
You would have to have a very good reason. So actually, let's do this thought experiment.
That's adorable. Your Mach number is well underneath 1.
Mhm. Um, this would be extremely computationally expensive. All right, so we would be looking like if we had our mesh. Let's see. You have to draw a picture here. So if we were just doing the wing, for example. I don't even know if this is compelling. Hang on, I'm better at drawing pictures than this.
Perfectionism kicked in.
I can't allow it. Okay. That's better, I think. Okay. All right, so if we were to do a 3D simulation of this thing, not green, maybe red. Okay, and this is our domain, which probably isn't even big enough to be honest with you, but let's just suppose. Okay, and so let's say that this domain is a bit longer than the wing. So let's say this is 2 meters by 2 meters by 2 meters. And we're saying that we would have our grid spacing delta x be on the order of it would be 6 times 10 to the minus 6 meters.
It's a uniform grid.
Well, we can do it if it's so if it were uniform, which would be insane, we would do some grid stretching probably, but
I'm gonna say, like, I thought you were implying that we're doing a uniform grid with that space. It's gonna be like, oh God.
well, Reynolds number of 6,000 or 6 million, I'm sorry. We wrote down
What the Kolmogorov length scale would be based off the Reynolds number.
Somewhere. I thought it was here, wasn't it? No. Yes.
It was up there somewhere.
I did do it, right?
Yeah, it was further up, I think.
Here. L R e to minus 3/4. Okay. Okay, can somebody tell me what 1.5 meters times 6 times 10 to the 6th raised to the minus 3/4 power would be?
Wait, what?
What do you mean?
Oh, sorry.
Is this what you're calculating?
Yeah, well.
Ratio.
$1.23 times 10 to the negative fifth. got two.
Mm-hmm. Yeah. Okay, so we could stretch our grid like a little bit, not a lot. Okay, so our grid size for a fully resolved turbulence simulation of this wing is going to be so let's say most of the domain is delta x equals the Kolmogorov length scale. Then
Oh, quadrum.
what?
Sorry.
We'd have, let's see how many
162,600-ish
per
per
direction.
direction.
Say it again.
162,601. That'd be the number of cells in each direction. You do 2 meters divided by 1.23 times 10 negative fifth.
Yeah. Which is how many cells total? Cube that.
4.3 times 10 to the 15th. All the grid cells. And you basically need about.
Plus some more for refining around the wing. Because we haven't resolved the viscous sublayer, right? So we'd have to add some more cells close to the wing.
This is assuming that you're using like an actual DNS simulation. Okay. Or DNS. Yeah.
Mm-hmm.
Doubled up on simulation.
So this means fully resolving equals DNS. At the wing to resolve the viscous sublayer. I don't even know, actually, I'm not even sure if this is possible. Hang on. Biggest grid solved on HPC to date.
That's done some really crazy ones with some of the rocket simulations.
Yeah, but 10 to the 15th is
Yeah, it's not like you have to store like velocity, viscosity, density, everything at each individual cell.
yeah. No, that's not what I want. I Googled the wrong thing. So as of 2025, the largest CFD simulation on supercomputers was 200 trillion grid points. Which is, what is trillion? Is that 10 to the 9?
Trillion is 10 to the 12.
12? Okay, so 200 10 to the times 10 to the 12. So 2 times 10 to the 14. So close, yet so far.
You can do it.
All for simulating something that somebody could just like go out and just do experimentally.
Maybe,
Tech- yeah,
but you couldn't get all the same information, right?
that is fair.
Notice I can't do this on MATLAB on my computer.
Oh, no. No.
I found out how angry I made my computer when I was running, I ran the 5% volume fraction case of the Real Bernard thing. And I was using 180 gigs of RAM, and the fan was going so fast that my computer was like heating the room to the point where I actually stopped it.
I destroyed a heat sink in my computer one time.
Like CFD, quite a few more stories.
I wouldn't have done it except for the cluster I ran on was down for maintenance and I had a deadline. And I was like, well, we'll see what happens. And then when I brought it to like the Apple store, they're like, what happened? I was like, I don't know. I must have had a lot of tabs open. I have no idea.
It's like one of those things where it's like, no, I didn't drop my phone in the toilet. Ignore that little indicator at the bottom that says it went in the water.
Yeah, so. So this is a problem. Um, and it's also why we will use the like law of the wall to help us. So to mitigate this, we can use so-called wall functions. In combination with turbulence models. To make problems like this tractable. Okay. I also wanted to, I have another little picture I want to draw. I'm gonna just put it here. It doesn't, I guess it's okay that it goes here. So if we look at the u component of velocity versus y, and then this is our surface, our wall, generally the velocity profile is going to look like this, right? That we all know and love. So velocity does this. What?
I'm familiar.
We're familiar, yes, yes, yes. Not a pretty picture, but that's okay. So up here is our turbulent layer. And then our logarithmic layer is going to be kind of roughly here. And then this itty bitty thing down here is our viscous sublayer.
Apologies if this was already mentioned earlier, but like, does this tie in with the boundary layer thickness? Like the models that they have, right, where it's based upon like whatever the -1/7 or whatever power laws for the boundary layer thickness.
So it is naturally related, but I don't think that the models are usually quite the same as that.
I just didn't know if this was like a breakdown of that, or if those were just like a good enough for getting stuff done if you're trying to like do a duct analysis or something like that, or.
I'm gonna say, so like the 1/7, like the power law ones that we talk about in intermediate fluid mechanics, just so you know. Those ones, I don't think they are like directly used in as like law of the wall models. Yeah.
Okay.
So it's related, but not quite directly translatable.
Sorry,
if
I
that
didn't know
makes
if was,
sense.
like, remotely related to this, but
No, I mean it is because we're talking about boundary layers and like close to walls, so it is relevant, but it's just I don't think the exact same.
it's not like a GSD method of when you need to calculate something, you don't need to be like fully resolved.
Mm.
Okay.
Okay, so where am I here? Okay, so these models essentially provide like a blending between the turbulent outer flow regime and then the inner layer. And then they're going to impose boundary conditions on the turbulence model. So basically we'll have this boundary condition at a spot kind of like a little bit away from the wall, if that makes sense.
So like it'll be like a pseudo boundary condition at the end of the viscous sublayer, and there'll be another boundary condition at the end of the, is the next one out?
Logarithmic?
Yeah.
Yeah.
Okay.
Yep. So these models blend between the turbulent outer layer and the inner layer. And they also impose boundary conditions on the turbulence model used. Mhm. Okay, so for example, wall functions for the K epsilon model impose the following. So they have that dk dn is equal to 0. D omega dn is equal to 0. Kw is equal to u tau squared over the square root of c mu times yw. And omega w is equal to square root of kw over c mu to the 1/4 times kappa times y. So this is a model proposed by Mentor in 2001. Okay, so the choice of wall model can change results pretty dramatically. Are you being sarcastic? I don't know. I mean, it's a pretty small layer. So I think for a lot of people, it could be surprising that like how you model like a 1 millimeter slice of the domain really matters.
Maybe I've just been like super jaded, but like just even micro scale changes in the surface finish, I feel like that could really severely affect how turbulence happens closely within the boundary layers.
Yeah. Uh, sorry, can produce dramatic differences when predicting complex flows. And notably, if there's flow separation, all wall models are questionable.
He is just like, oh.
Yeah.
No, I'm doing great.
You're doing DNS, so don't worry. So the least wrong. Do you guys not know the quote about modeling? Probably not. I need to look up who said this though. I think it's Feynman
It's always Feynman.
because he's awesome.
Actually, like.
Who said that?
The Feynman quote about fluid mechanics, it's pretty awesome. You probably heard of it many times.
Oh no, it wasn't Feynman. It's a statistician named George E.P. Box.
Fox.
Who said that all models are wrong, but some are useful, which is true generally. And I'm gonna write it because I like it.
What was it Feynman?
What is it?
No, This is fluid dynamics. Even people who study it don't understand it.
That's rude.
You should be a little better about it.
I mean, not to the level of badass she is remotely, but yeah, I also feel that too. So.
No one understands everything.
These stories are interesting.
What?
I'm not gonna edit this out just to shame you.
I might not. Okay, so the least strong method is chosen usually by comparing with experiments. If you don't have experiments, you're on your own. Kind of.
How do you even determine that experimentally on that small scale?
Oh, no, I mean, like you could look at large scale behavior.
Okay.
Yeah.
Basically, like a lot of like PIV definitely wouldn't work, and like most of the visualization techniques would require like a crazy high resolution camera.
Yeah. So, okay, I should write this down. So if using a wall model, you can place your first grid point at y equals around 30 y plus. Okay, so you can have just your first grid point in the viscous sublayer, but it doesn't need to be, at 1. So this is the benefit of using one of these models, which might be wrong and disastrous, right? Or you can avoid wall models by refining your grid to y plus equals 1 to resolve the full boundary layer. This is what I typically do. If you can. Obviously, this is highly Reynolds number dependent. So
As we found, tool dependent as well. And GHG did not like the group stretching with the thermally evolving flows.
well, that could have been an us issue.
That could, it was probably a me issue.
This is Reynolds number dependent.
There you go.
Right, it's a team, it's a group project.
Makes me feel better.
Let's see. I might. There are pictures that I kind of want to show you. Hang on, let me see if I can just send this website to the iPad. AirDrop it. It's hot in here. Okay, so maybe this will load. Okay, hopefully you guys can see this. So these slides have a nice kind of suite of examples of kind of the effect of different wall models in here. Okay, so the first one, this is using a K epsilon turbulence model. And we're looking at rotocraft ground effects. So I've not read this paper, but essentially what you have in this kind of like this, I can't point on here. So the like grayed out image in the middle, that's a helicopter. All right, so this is essentially studying like the effect of the propeller on fluid transport, right? And then these are at 2 different height locations. and we're looking at different slices here. This study cared about rotor loads and ground shear stress. So I'm guessing that they were caring about brownout. So that's like the dust that gets kicked up when a helicopter is taking off and landing, which can be very problematic. What?
So what Max is working on?
He was.
Okay.
I don't know if he is anymore. He might be is he graduated? I don't know. Yeah, he was at one point. Yes. And this study chose a model by comparison with impinging jet test cases. So basically a jet of air impinging on a dusty surface, I assume.
Is it impinging perpendicular or just?
It can be down. Yeah, so like if this is the ground, impinging is perpendicular.
Okay.
Yeah, so if you like had a compressed air hose and you just blow it straight at a dusty
I
ground.
just wondered if it meant exactly normal.
Oh, yeah. Impinging doesn't necessarily need to be normal.
Okay.
It's just, to me, it means just like hitting a surface.
I've never heard that.
No? What about 3500 lab?
I've never said impinging.
Yes.
She didn't say that, not that specific word, but that idea.
Okay. I don't know if I believe you. I'm just
I have
kidding.
you, it doesn't, it's okay.
No,
Fix
it's
everything in intermediate fluids.
it's fine. Yeah, impinging just means acting upon. Okay, so these three different slices show three different models, turbulence models. So I think we talked about K epsilon for sure. We talked about Splart, Almaras, and I think I mentioned the Baldwin Lomax one too, but all of these velocities are scaled the exact same way. So they go from 0.05 to 0.95, and you can see, there are differences here, obviously, right? And then, I guess I'll just say this. So these 2D color maps are nice to communicate things. And like in this case, it does a pretty good job of showing the differences, but a lot of times 2D color maps can look very much the same and not be the same, like deeply. Were you and I talking about that?
I don't know, but
I was just talking about this with somebody.
I
It
don't
might have been
know.
Jacob. I think it was Jacob. So what's often done is doing a plot like this, for example. So at a specific location, you look at the vertical displacement and then the velocity profile. And so this will highlight huge differences that might exist that are kind of masked by just a 2D color map. So here the experiment is red lines with the red circles on it, and then our different turbulence models that they studied are in pink, orange, blue, purple, and green. And then you can see at different locations, so left to right, those different equations, various models do better with the experiment under different conditions. So like if you look at the far left plot and the middle plot, you might say, wow, like that orange dashed line looks pretty good. Maybe even the pink one is decent. And then you look at the last plot in a different context and they're terrible, right? So, yeah. Also, this is a good note that they make on these slides. The study used a pretty coarse mesh, so that's going to exaggerate effects of the turbulence model that you choose. And then, so that was kind of a demonstration of maybe some failures of turbulence models. Here's an example of success. So Reynolds average Navier-Stokes. So when we averaged the Reynolds, oh my gosh, when we Reynolds averaged the Navier-Stokes equations, we ended up with RANS, okay? And since that tool solves for average quantities of interest, it is like this says, the frontline fluid dynamic design and analysis tool. So it makes doing simulations that are big pretty cheap. And it can do a pretty good job. So for this example, this does a pretty good job for looking at body forces on complex geometries, including high Reynolds number and high Mach regimes. Obviously, if you were looking at high Mach, you would have to do the compressible version of RANS, which I did not show you, but essentially it's the same kind of process, but you keep density in all the averages and you care about density fluctuations too. And then you also have to solve a energy equation. So problems like these. So looking at pressure contours on a shuttle or shock waves, it looks like on a high-speed aircraft. And I think I kind of want to end it there. So I'm going to leave it at this for our turbulence unit. Hopefully you guys feel at least a little more equipped to do kind of like statistical analysis of turbulent flows, have a sense of if you wanted to do like a simulation of turbulence using models, how you might go about that, and then also have an understanding of if you wanted to develop your own turbulence model, how that kind of arises.
Is there just like a website somewhere with every turbulence model? For a bunch of
Like a
different-
single website?
That would be dope.
There's a.
ANSYS probably has like all of the CFD packages probably have a summary at least of what their code packages include, but honestly, there are so many, especially like recently, now that like data-driven and machine learning modeling has become a whole thing. There's tons and tons of models that people have proposed kind of in the scientific literature. So like, I don't think there's actually a repository of every single model that exists, but like a lot of the ones that get proposed in the literature, in my opinion, at least recently have been kind of the nature. We did a bunch of DNS. We put it on into a neural network and we like can fit the curve, right? But which is fine. That's fine. But then they don't put it inside of a RAND solver to see how it does.
NASA JPL also has a bunch of really good.
Yeah, that's true. The NASA websites are good for like the historical, like the classics in terms of turbulence models. So if you wanted to look at like the Szilard-Almaras model in more detail, or the like NASA websites or CFD packages tend to summarize them, or books like these. But yeah, like the fact of the matter is there's always like new models being developed, so it's hard to have like a currently updated repository of all the things.